Hello, my name is Stanley Starr with Imperial College London. I would like to discuss with you today the viability of mining ice on the moon. One of our motivations for mining the ice or mining anything on the moon is the tremendous amount of rocket mass required and thereby cost to take anything to the moon's surface. And you see here a particular figure, 153 kilograms to get 1 kilogram on the moon's surface. So we're very motivated if we can find resources at a destination to be able to harvest those resources. The moon is covered with a very fine material called regolith, and it's made up of volcanic materials. And there's been a lot of effort put into converting regolith into oxygen and metals. That's not the kind of mining I'm going to talk about today, but it's very important. But what is important to us is if we put water ice in regolith, what are its mechanical properties? If we look at the poles of the moon, and here's a shot by JAXA satellite, we see craters that are in shadow, many of them permanently, and then rims of those craters and mountains which are in sunlight quite a bit. And the Earth is on the horizon and rises up and down in one location. And the sun goes around the horizon, sometimes dipping down at a particular location, sometimes dipping down and sometimes coming up. Looking at the poles at the South Pole, we see these permanently shadowed areas. On the larger image to the left, in a more close-up image, this is the availability of sunlight in percentage, and the brighter areas are about 80%. So there's a fair amount of area near the South Pole that gets much more sunlight than you would get in the 2 weeks of sunlight and 2 weeks of darkness on the rest of the moon. So there's a variety of advantages for actually locating bases on the South Pole or even the North Pole, but the South Pole is much better of the moon. Now, in 1998, a neutron spectrometer was flown to the moon in orbit around the moon, and it discovered very large amounts of hydrogen at the poles. And the question was, is that hydrogen water or is it solar wind implanted hydrogen? And to answer that question, NASA sent a probe called LCROSS, which impacted a Centaur upper stage into a permanently shadowed crater near the South Pole called Cabeus, and looked at the plume of material that came up into the sunshine. And as that material was excited and re-radiated, a lot of information was gleaned about that, including more than 5% biomass of water, plus there's a lot of other impurities that we would need to worry about in order to use that water for any intended purpose. So there's a tremendous amount of information there. A lot of remote sensing has been done by subsequent satellites of the moon. This is bolometer readings of temperature. What we see is that these cold traps in these craters are the coldest spots that we've measured in the solar system. And the reason that they're cold is that the night sky is extremely cold, about 3 degrees Kelvin. There's no sunlight coming in to heat them up, and there's just a small amount of geothermal energy produced by the moon. These cold traps are cold enough that if a water molecule sticks on the surfaces, the residence time is millions to billions of years. So they accumulate water over a very long period of time. It was also more recently discovered by analyzing several data sets that there's surface frost in a number of areas at the poles of the moon. And this is very exciting. That means if we go there in these areas, we'll actually see white frost on the surface in these locations, which doesn't necessarily tell us about the total mining potential, but it is indicative of how rich the area is. Now, we normally think of mining in this kind of scenario, and this is regolith mining for either the moon or Mars. But if we disturb the regolith with ice in it, we're going to very quickly lose that ice to sublimation into the vacuum. So we need to figure out new methods to do ice mining, but we don't have enough mechanical data from the poles of the moon to determine how we might do that. One concept that has been floated is to put mirrors on the edge of of craters to shine light down to keep our mining equipment warm, to provide heat for power, to provide heat for vaporizing water, to provide sunlight for power, et cetera, et cetera. But this is an area where a lot more data and innovation is required before we can actually start building prototypes. And the key data that we need is, what are the mechanical properties and what is the fine distribution of the water ice? Here are some concepts, architectural concepts of how water ice might be mined and brought back to processing stations and so forth. But again, this is really too early because we don't know enough about the mechanical properties or the fine level distribution of the water. Here's a much more large-scale architecture of a commercial mining operation that would be able to produce propellant materials and transfer them and sell them in a variety of orbits within the Earth-Moon space and perhaps beyond, which is one of the large-scale potentials. If we look at the value of the water, if we monetize how much water that is and look at it from the standpoint of the cost of delivering water to the moon, and then we also look at the mineable water on the moon, which I estimate to be 10% of the amount of water believed to be there, although that number has increased recently, we get some really, really large figures. Of course, this depends on our ability to actually capture it, get the impurities out and create something useful with it. And it also depends on a market. But certainly there would be a market for using those resources locally to support scientific research stations and that sort of thing on the moon. Before we can decide how to do it, as I said, we need to determine more information about the water distribution and the soil properties. There's a number of projects that are planned, and here are some of them. The one I'm going to talk about, the one that I was involved in for many years, was Resource Prospector. This is 2015 field testing of a rover prototype, and my group at Kennedy Space Center provided the payload, the drill, the instruments, and that sort of thing for this rover. And the idea is the rover looks at the ground with an infrared spectrometer and a neutron spectrometer. The infrared can just see the surface, and the neutron spectrometer can see about 2 meters into the soil, prospects around for the distribution of water, and then at a site of interest, drills into the surface and brings out samples that are then put into an oven system and then into a GC mass spec. This project was canceled and replaced with Viper. And what was learned in vacuum drill testing is that instead of having all the complicated oven and valves and all that, we can really just put a mass spectrometer pointed at the tailings of the drill, the auger drill, as they come up. And we can estimate fairly accurately the amount of water that's in those tailings. And of course, we know the depth. We know the amount of mechanical energy required to drill and bring up that material. So we learn really the information that we need to know. Viper is planned on launch in 2023, late 2023, and is meant to last about 3 lunar days. And we'll try to drive around as much as possible and stay in the sunlight. And the M-Solo instrument is this mass spectrometer, and this was produced by the team that I worked with at Kennedy, and the principal investigator is Dr. Janine Captain. And in short, in summary, if we could capture that water that we know is there, we can enable much more sustainable living on the moon, all the way to potentially a hardy commercial environment. Thank you very much. I appreciate your attention.